All right. Now, first lesson today on circle geometry is going to be sort of straightforward in a way because you're going to really dig deep in your brain, your memory, from year 9, actually from year 600, 6, 7, 8, 9, and 10. All right? So, but I'm sure you'll be all right. Okay, so today you need to recall and relearn the structure of geometric proof. How do we write proofs? You should have learned it from year 9 and year 10 when you're writing your proofs for similar triangle and also congruent triangle. Alright, can you all remember that? The structure is basically the same. So we'll relearn all this, recall and relearn all this. Now, recall what you've learned the last few years. Then we're going to be able to define and prove the central angle theorem. Okay? Understand the different cases of central angle theorem and be able to use the central angle theorem to solve numerical problems. What I want all of you to do is read your booklet. Alright? We're going to go through the first few weeks. Think about proof. Think about the first two pages, page 2 and page 3 in terms of the assumed knowledge. And then we'll look at page 4, which is central angle theorem. Now, before that, what we need to do is learn a few new words. You should know the word definition, but I'm sure you haven't seen the word axiom before. You might have, or lemma, theorem you have seen. So these two, basically, we need to understand a little bit. So definition is a statement which need not be proved. Alright? So we define certain things, we don't have to prove that. Axiom is a statement that's accepted as being true without the need to prove. Lemma is a true statement that can be proved. And theorem, a statement that can be proved to be true using acceptable definition, axiom, lemmas, and other proven theories. Alright? So with this, you don't have to copy it down because I will upload this on campus. Just make sure that you know that we're going to go through a few more things. Do not write it down. No need. Alright? Now, we need to think about proof by deduction in what we are doing. We're going to have steps and then deduce. So the truth of the theorem is arrived by reasoning for other accepted truth. The validity depends upon the correctness of the axioms and the theorems used to deduct it. So we need to think about how we're going to arrive at the conclusion through the reasoning. So it's from what we've done, writing out all our reasoning and then proving deduction. Alright? So, example of writing a proof for similar triangle. Now, I'm not sure who have been to my class. If you were in my class in year 9, I would have stressed this as being really important. So the structure of it, the example, it's just like writing an essay. You've got an opening statement, an introduction, required to prove. So in this case, I want to prove that triangle DEF is the same as triangle PQR. Alright? So you need to have statements. What are the statement? So statement in here, in triangle DEF and triangle PQR. So DEF and PQR, I haven't labeled this yet, but you'll be able to deduct from here, right? So angle DEF is the same as angle PQR equals 35 degrees. So example. So why? Because this is the reason it's given in the diagram. So it's given. Second one, this is the same angle as that, 72 degrees. Again, it's given. Now, you need to give the third reason. Proving similar triangle, reason number 3. This angle will be the same as that angle because the sum of internal angles in the triangle equals 180 degrees. See the steps. And then you can conclude. Therefore, DEF is similar to PQR, AAA. Angle, angle, angle. Yeah? So these are the structure that you need. It's writing an essay, writing an argumentative essay like opening statement, introduction, and then your reasons and everything, and then finally your conclusion. Yeah. Happy with that? Now, let's go on. This is what is given in your handout. Structure that I want you to think about is basically the same as what I've done in the previous slide, which is this. Alright? So you've got things like required proof, the proof with the reason, and then your conclusion. Alright? So go through it at home, read it later. But here, see, we got a statement, and then proof. Provide mathematical justification. Important, mathematical justification. We are talking about maths. Okay? So it's all mathematical reasoning and thinking about it. Alright? Are you all happy with that? So what we're going to think about is using all these angle properties, angle sum, triangle properties, quadrilateral properties, and circle properties. Yeah? Okay. Now, this bit you should all know. Agree? I don't really have to go through what is an acute angle, what is right angle, what is obtuse angle, what is a straight angle, what is a reflex angle, and what is a full rotation. Do I? I don't need to. Okay? Just, you will get it, so don't bother copying it down. Once I release it on Canvas, you'll get it. Now, what's the difference between supplementary and complementary angle? Oh, yes?
One of them has the 90, one of them has...
Which one? Which one?
Complementary 90, supplementary 90.
Thank you. Alright, I know one of them adds 90, the other one adds 180. Alright, so you need to be able to say that complementary angle or supplementary angle. Alright, so that is important. This is one of the basic things. Because when you're looking at, later when you're looking at a circle, you have this sort of situation. Alright, this is the bit that I really like because I think I did quite well in this part when I was in high school. That was many years ago. Alright, the next one. You must know your parallel lines and angles. You need to know what are corresponding angles, what are alternate angles, and what are co-interior angles. Alright? And then of course you need to know vertically opposite angles. Here, I'm pretty sure you have used a lot of this in your triangle proof. Yeah, remember that? You would have used corresponding angle, you would have used alternate angles, you would have also used co-interior angles. And of course the vertically opposite angle. Alright? Vertically opposite angle just means that the two of these, the vertices meets at this point, that's all. It doesn't mean that it's vertical. Alright? Just remember that. So that angle is the same as that. Corresponding, this angle is the same as that. So the alternate angles is like a Z shape. So you can see that it could be something like this. Alright, this is the same as that, the Z shape. Or it could be this way. This angle is the same as the angle. Yeah? Okay. Next. I'm bringing all this back, recalling everything from my memory. Okay, next bit. Types of triangles. You need to know equilateral triangles. You need to know isosceles triangle. You need to know scaling triangles. All equal sides. 2 equal sides and 3 equal sides. Now from there, I am going to split it again to something else. Alright? Have a look at the next slide. Here, you've got what I've shown you just now, equilateral, 3 equal sides, 2 equal sides, and the scaling. There's no equal sides at all. Now, then, I classified this by internal angles. Alright? Equilateral. You can never have right angle triangle as a equilateral triangle, right? Are you sure? Definite? Seriously? Yes? Yes, that's right. Unless you're in a spherical form, then you can have equilateral 90, 90, 90. Alright? But we're not going to deal with that. We're only dealing with 2Ds. Alright? Now, only dealing with 2Ds, so you need to know that isosceles triangle, you know that the base angle are the same. Alright? Wording, base angle of isosceles triangle are the same. Wording of that. Alright? You could have acute, you can have obtuse, you can have right angle. Alright? Right angle triangle, right angle isosceles triangle, 45 degrees. That's the most straightforward. And then scaling triangles, no equal side. That you would typically know, like Pythagoras' theorem, 3, 4, and 5. This one, you've got one obtuse. This is not the same as this, not the same as that. And then, of course, the rest. The other one, all acute angle. Alright? So basically, I split the triangle out a little bit more. Next, quadrilateral. Of course, you need to know rectangle, trapezium, kite or rhombus, and parallelogram. Okay? And remember, this is important, the sum of the interior angles of any quadrilateral is 360. Eventually, we're going to think about the quadrilateral in a circle. Right? When all the vertices touches the side of the circles. We'll do that, I think, next week. And of course, circle. You should know circumference, you should know the center, you should know the radius, you should know the diameter. Yeah? So what I've done is here, I've basically summarized all whatever you need to know from the first few pages of the book, and you can really transcribe it into your book a little bit later and do whatever you like. Right? From there, circle again. You need to know what is the minor arc, what is the major arc. So the minor arc is just this bit here. Alright, you've got the radius, and this bit is smaller than this bit. Therefore, this is minor sector, and this is the major sector. And this is the minor arc, this is the major arc. Okay? All this knowledge is good because later in 11 methods, you will be requiring some of this as well. Once you know all this definition, you'll be all right in the later part of your methods. All right, now, year 9, similar triangle proof. Angle, 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 side, 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 side angle, side, and right angle, hypotenuse, and side. Now, really remember something. SAS can never be ASS, all right? Why? Why can't it be ASS? Apart from it is not such a nice language, that angle has to be in between two sides. That's why it's SAS, right? Okay, so it cannot be ASS, remember. Cannot be this angle and this two sides. This is okay, because you got right angle, hypotenuse, and one of the sides. Whereas this one, no. Right angle, that's fine. Okay? Okay, keep going. Congruent triangles. Again, same thing, side, 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 angle, 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 side, and right angle, hypotenuse, and side. Not going to go through all of it because I assume this is assumed knowledge. Now, do you have any question for me at this stage? No? Let's go on. Move on to the next bit. The circle theorem number 1, central angle theorem. Alright? The angle at the center of a circle, subtended by an arc, AB, is twice the angle at circumference subtended by the same arc. right? Long definition, but basically it says, if you've got the angle from point A to B, all right? A to B, if I draw the angle, draw a line, the radius, that angle here would be double the angle from point A to B, touching the circumference. I'll prove it to you in a few minutes. Now, the word that you probably have not come across is subtended. Next slide will show you what does that mean. Subtended angles. An angle within a circle is created by two chords meeting at a point on the circumference of a circle. The diagrams below show the angle subtended by arc AC from point B for two different circles. So, the arc is AC. Alright, point B. Arc is AC, point B. Just basically, the subtended angle is you've got two lines from the circumference by an arc. Alright, that's it. This I like these diagrams. This actually show it very clearly what the subtended angles mean. Alright, now how am I going to prove that this is double that one? Right. One thing for proving angles. For circle theorem, if you look at a situation like this, what I would do is I always will start from the center O and draw a radius up to this point. Why? Why would I do that? In a lot of proof, you will need to be able to do that. Why would I do this? Why would I do something like this? Alright. Why would I do something like this? Why would I construct a line? Yes?
Because you can use the radius all the same, so it makes like plenty of isosceles.
Thank you. That's
And then you can make lots of triangles, so that x would be the x down the bottom, and then the other side of that would be.
very good. So you can see that if this is radius, this is radius, this is radius, this is isosceles triangle, correct? This one, that will be another isosceles triangle, that will be another isosceles triangle. So it's quite important in terms of proving. Yeah? Some of the more difficult one, more complicated one, generally if you use that strategy, you will be fine. Alright? Let's go and see what we are doing. Proof of this. So what we are required to do is required to prove angle AOB. AOB is twice the angle of that. Okay? So basically, this is 2x, this is x, right? That's given that points A, B, and C are all lie on the circumference of the circle with the center O. Alright? If A is somewhere here, it doesn't work. A and B should be just right on the circumference. Alright? Not that I've drawn it nicely, but that point is A. That line should touch that. Alright, so the proof. I'm going to do it step by step. First, construct a line from O to C and let angle ACO equals alpha, BCO equals beta. It's up to you how you want to name those angles. I don't mind. You can name it A, B, or theta and gamma, or whatever. Alright? I just use what I'm so used to, alpha and beta. Now, the proof that Sandler uses is slightly different from what I do. Okay? But it's correct. It's the same thing as well. Yeah?
Is there a notation for line?
No.
You just have to write a line.
Yeah, just construct a line. There's no notation for that. I just use that construction. Yeah. Yeah. Sometimes we can be lazy, sometimes probably not. Alright? So now, here, I say that OA equals to OB, which is the radii of the circle. Correct? Yeah? And OC as well. and therefore OAC is an isosceles triangle. So I should have used OA and OC. I typed it incorrectly. It should be OC. Alright? Because I want to show you that OAC is an isosceles triangle. I'm going to start off with one triangle. Yeah? Switch off your phone or put it on silent, please. So we're going to look at one cycle, so there should be an OC. Alright? I started off with OA equals OB equals OC, radii of the circle. Then I decided to change my mind, so I got rid of the wrong one. So OA equals OC, which is radii of the circle. The purple is the reason. Always state the reason when you're proving. So from there, I can conclude that OAC is an isosceles triangle. Right? Logical? See the logical steps. And then from there, hence, OAC is the same as OCA, which is alpha. Then I give the reason, base angles of an isosceles triangle. Yeah? Step by step. And so, COA is therefore equals 180 degrees minus 2 alpha. Angle sum of a triangle. Yeah? Got it? So now I found this. Right? Now, do I really have to repeat the whole process for OBC? Not really. I can just say similar reasoning for triangle OBC. Because it's obvious, you're using the same idea. And therefore, COB is 180 degrees minus 2 alpha, 2 beta. And at point O, AOB equals 360 minus that, sum of angle at the point. And therefore, AOB equals to whatever. And AOB equals to 2 alpha plus beta equals to 2 alpha plus 2 beta, which is 2 alpha plus beta, therefore, which is 2 angle ACB. QED just means that it's proven. It's Latin. I'll give you the full whatever of QED next time. Alright? Now, there are many ways of proving. The book does it, Sadler does it in a different way. Alright, now this is my proof. I did it this way. Like I said, Sadler did it a different way. It's up to you whether you want to, if you need to prove this, you can either use this way or use Sadler, or there are many other ways of doing it, I'm pretty sure. So what Sadler did was, he extended, instead of just drawing OC, he extended this line out. Work out this angle, and then work out this angle. Work this angle out, and work this angle out. And add two of them together, and show that that is 2 alpha plus 2 beta. So again, it's the same way of proving. As long as it is logical, as long as it's correct, that's fine. I'm not going to worry about it. We can, I can say, in this sort of situation, if you need proving, I remember marking some of the year 9 proofs, and when somebody does it something different from what I do, I'm going to really think about how it is proven. Alright? Now, what I want all of you to do is mark your proof. Okay? Based on this circle theorem 1, can you think about the 5 cases of the central angle theorem? I will give you about 3 or 4 minutes to talk about it. If you want extra piece of paper to draw it, happy to give you more paper. You don't have to draw on your booklet yet, because you might want to discuss and think about what you want to do. Alright? And then you can copy it down. Alright? So think about what. Alright, think about the 5 cases. What do you have? I've already given you one. This is already one of the cases. Alright, you know that. This is already one of the cases then. Here, you want extra different color pens? Pencil? Here, I've got.
Finish more?
Right, I don't know how I should do that. You want to drop that? You want to use this? Go ahead. You want to use this, but give it back to me later. You want to use this? No worries. All right. The 5 cases. Last night it took me a while to think of 4 cases, and finally, the 5th case, I found it. So you've learned the first theorem. There are quite a few theorems going. Like I said, please don't go ahead and do your book idea. It doesn't matter if you can't come up with all 5 because I haven't given you a lot of time. But you know for sure this is one of them. It's a Latin word. I'm going to look for it now. Look it up. I know what is the meaning, but I don't actually really know what exactly
The next one is, was this?
Yeah.
So QED.
It just depends on where all the
All right, that is QED in Latin.
that which
In Latin. So that which was to be demonstrated. So you demonstrated it, that's why it's QED.
also basically myself up.
It's in Latin.
Wait, sir. So is that basically just being hence or therefore?
No, it's not as well, just that it has been proven. What needs to be done?
So you have to say that at the end.
Sorry?
You have to say that at the end.
Ah.
You're saying conclusion.
It's just, I do it because I've been trained to do that way. You should QED. Alright, if you want to write it down, write it down, but I will put it on.
Like, this.
I'll put it on our news feed.
This angle here. I mean, this angle here is become this angle here. Yeah, flip around. And it works the same for this one or this one. This one. I don't know. Maybe just talking about it.
Because I know there's a case where it's like.
Oh, I didn't know it was here. Oh, I didn't know he had my last one. I didn't do it.
It's the same color. On my ear.
Alright, this It's on a finish now. It's sweet now. What does it mean?
Yeah, I have one people who have one, and he has one out of them.
And it's good this way.
Right, everyone, let's come back to concentrate on the whiteboard, please. So, this is case number 1. I'm going to show you all 5 cases straight away. Alright? You've got a situation where this is the most obvious. You can see that this is alpha, this is 2 alpha. Now, this one here, you can see that this is the diameter. Alright? So the diameter touches point P and comes to point A. And then from here, O to A. Therefore, you can see that this angle is half. This angle is half the angle of that. Alright? That's the center. That is the circumference. Alright? So this is the one that last night I was cracking my brain. I couldn't work it out. But took me a while. Finally got it. Then this one just means that this angle, this point P here is just slightly below O. Still basically the same as that. You can move it around and it goes down. Alright. This one, not quite intuitive, but you can see that you're looking at the angle here and coming back, this angle here. This angle is actually double this angle. And finally, this one, I will prove it to you again, which is that is the diameter, because it's 180 degrees, this is 90 degrees. So I'm going to show you a different proof tomorrow that a triangle with diameter as one of the sides and both meets at the circumference, that will give you 90 degrees. Alright, I will show that to you again tomorrow, a slightly different proof. You can use the central angle theorem to prove if you want to. Now, I'm going to go through a couple of examples with you. At the moment, the example hasn't asked you to prove yet, but I'm writing the proof so that you understand where I'm coming from. Alright? So, 4 circles that I've handed to you, the worksheet. Let's think about example 1. You are asked to determine the size of angle BAC. You know that it will be half of alpha, correct? 70 degrees. Okay? Now, at this stage, like I say, you are not asked to write the reason yet. But, if needs be, you must say angle at the center is twice the angle at the circumference. That is the standard reason that I want all of you to give. Alright? So try the next 3 please, example 2, 3 and 4, and then I'll go through it with you. So remember, give a reason. Although I did not say give a reason, I want you all to start learning how to give a reason. Alright, second one. I've been looking at that. You should know what this angle is. Alright? Of course, it's double that. And then again, I give the reason. That's all. Generally, question like this, we will ask you prove, and then at the end, hence or otherwise, what is the angle, all this sort of stuff. All right. All right. Example 3. Now, you know that CAB is 150 degrees. What is this angle? You need to think about that first, don't you? Using this one here. Two-step process now. So you know reflex angle, BOC. Now I mentioned the word reflex angle because if you say BOC is this, you want to say that it is a reflex angle which is out there. Alright, the reflex angle is 2 times 150, 300 degrees. Again, I give a reason, and then BOC is therefore 360 minus 360 degrees. Sum the angles at a point equals to 360. So think about it logically, step by step. We'll really have fun with this eventually. I mean, the way that you prove certain things will be very different from the way that I prove. Alright? I mean, some of the things you will do the same thing as I do, but some of the things probably not. But it's okay, that's part of the thing that I want all of you to think about is proving is not always one way. It's not one size fits all. Alright, last one. I'm going to keep my mouth shut. This is a slightly more complicated one. Yeah? Hmm?
So for these two here, wouldn't those be the same thing? No, it is.
This is, you're looking at.
Yeah, it is the same thing. If you connect A and B.
Yeah, you connect A and it's the same thing, but you're not. You just need to have your head. The slight difference here is you connect A and B, yeah, it becomes there. But we're not looking at that angle, we're looking at this angle.
Yeah, but if you connect this angle, it's like literally just like the same diagram. So the
Yeah, I understand
so
that.
the fifth diagram should be like this one here. Instead of this, then now, just do it like this.
Right, this is whatever.
Yeah.
Alright, this one you need to make use of the idea of the radius. Alright? So you know that OB equals to OA is radius of the circle, and OAB is therefore an isosceles triangle. So OBA equals to OAB equals 41 degrees, base angle of an isosceles triangle, and therefore you can work that out. Or if you don't want to use the central angle theorem, you can work out this angle, and then sum of the angle in the triangle is 180 degrees, work this sum angle out, and that. That's fine as well. Not an issue. Right, many ways of solving one problem. Now the next one is the sort of the more important, not the more important one, it's what we really like you to know, is when you use a central angle theorem. The statement we use as reason is angle at the center is twice the angle at the circumference. Alright? Now, pretty straightforward first lesson, but a lot of memory that you need to rethink about what you have learned. Alright, I'm going to stop here, and you've got some exercises that you need to do.